Hello teacher, my name is Nguyễn Võ Trường Toàn. My SID is F3979056, and today I will demonstrate to you my two games for the assignment 2, which are the A-star pathfinding and MCTS algorithm. So let's play the first game. So gonna let's put the music off. So here we have the main game world displayed as a grid. So here I have the main world displayed as a grid. The background is an animated lake with the red frog as an agent. Each grid cell is 32 by 32 pixels, and this grid is used directly by the A-star algorithm. On the right side is a A-star debug panel here. You can see it shows the start node, the go node, the path length, the total cost, and the numbers of open nodes and closed nodes. I also put the controls guide here. So when you left click, you set the go or you move the go. So I draw the go at the beautiful lotus with some blinking effects. And when you right click, you toggle the obstacles or the walls. I used some stones here. Or you can hold the right click to paint it or erase it. And A to run and R to reset. So for now, the rule is that you cannot put the go and the stone on the same node because it will cause a bug like this and you cannot do anything else. Have to reset it. And while the frog is moving, you cannot set a new go. You have to wait for it to finish the path. For example, here, I cannot put the new go until it stops, until it finishes, and then I can put a new go. Okay, I can start from here. So in this game, the path cost is calculated using an octile distance model. So that means diagonal movement is slightly more expensive than straight movement. So even if a path looks visually shorter, A-star may avoid it if it uses more diagonal steps and results in a higher total cost. I use octile distance because movement in this game allows 8 directions. Octile cost better matches how the character actually moves on the grid. Manhattan works well for 4-direction movement, and Euclidean is continuous, but octile gives a more accurate cost when diagonal movement is allowed. So let's talk about how to run A-star and how to visualize it. So when I left click and then I press space, the game converts the frog's current position and the goal position from the world coordinates into grid coordinates. So the A-star then runs on the grid and then returns the final path, which I draw some animated lady path to indicate it. And the open nodes, which are the path that haven't been discovered yet, I show it in yellow. And the closed nodes are the path with have been discovered, but they are not the optimal ones. So I show it in purple. So let's see. For example, I put some obstacle maybe. So press here. Here you can see the yellow part. They are the open, the path that haven't been discovered yet, and the purple ones are the path that have been discovered, but they are not optimal. And the chosen one is the lily pad one. Okay, so let's talk about movement and steering. You can see the frog, it just move very smoothly, right? It jump step by step. I used the arrive steering behavior. I reused it from the previous assignment. Each grid node is converted back to a world position, and the frog moves waypoint to waypoint until it reaches the goal. Once the final node is reached, the frog then snaps to the center of the grid and then stops. Let me try here. You can see it's gonna move. It's gonna jump very smoothly with animation and then snap to the center. And I also implemented a dynamic replanning obstacle function. For example, when it's following the path, when I put the obstacle on this way, like this, as you can see there, if I add obstacles while the block is already moving, the game checks whether the current path becomes blocked. If it is blocked, a star automatically runs again from the current position to the same goal. Add a new path, and a new path is generated in real time. This makes the movement adaptive instead of static. So now let's go to game number 2, which is the Connect 4 using the MCTS algorithm. Let's play it. So here from the menu, you can choose 3 modes. Yeah. So, but I mainly focus on the human versus AI and AI versus AI mode. Yeah. The human versus human mode are from the starter code. So before starting the game, I'll quickly explain the UI layout. So you can see the board is in the center, and each player has a side panel with the portrait and the status indicator. The active players panel is highlighted, so it's always clear what it is. Messages and game status are shown at the top of the screen here. And before starting the mode include AI, the UI asks for the number of MCTS iterations. So the input is constrained to the minimum of 10 and the maximum of 2000 to prevent invalid or extreme settings. So let's put one here so you see the warning. The minimum must be 10, and I cannot put more than 2000. Okay, I cannot. So this ensures the AI always runs within the reasonable range and keeps the gameplay stable. Let's put it 100. I play first by clicking on any column here, and you can see the piece, the gem, use gems here. The gems automatically drops to the lowest available cell. So let's put here, you see, it's going to be here, and when I put here, it's going to be here. Yeah. And after every move, the game checks for the wind. It could be horizontal, could be vertical, could be diagonal, or maybe or even a draw if the board is full and no one wins. When it's the AI turn, you can see the AI's thinking indicator on the UI here, AI thinking. And for the MCTS stats, you can see the UI display the MCTS statistics above each column. I have here column 0 to column 6. And the V stands for the visited, how many times the column has been visited. And here is the win rates of each column by percent. And at the top of the board, you can see the chosen column is highlighted. And along with that, I display the UCB score used to select the move as well. This UCB value is always shown even if the move immediately wins the game. So the UI explains every AI decision using MCTS statistics. Let's play until someone wins. You can see now I win. So when a player wins, the game stops immediately. The 4 winning cells are highlighted and animated. You can see with a blinking effect. The UI also shows a clear win or draw message. Here you can see I win, you say you win, and gives options to restart or return to the main menu. So press R to play again and press escape to return to the main menu. For now, I'll just return. And now I'll switch to the AI versus AI mode. Here, both players are controlled by the MCTS, and the game runs automatically. So let's put 500 maybe. So you can see the bigger the number I put for the iterations, the smarter the AI is. So when it's smarter, it will try harder to block every possible move that could make the opponents win. And you can still and you can see here the same UI elements. So I want to explain a little bit more detail about the win rate and the visited. Let's put here the minimum of 10. Yeah. For each column, the AI tracks how many times it has been visited and how often it leads to a win. So as you can see here, so you can see the total visit of all the columns is 10 and the win rate is under it. So the chosen column is calculated by using this UCB value here. This UCB value balances how promising a move is based on the win rates and how many times it has been explored, it has been visited. And combined together, it decides which move is strong and make that move. And maybe I can go quit here. So overall, these two games show how AI techniques can be applied in interactive gameplay. The A Star demo focuses on pathfinding, and I implemented also the dynamic replanning, while the Connect 4 MCTS game focuses on AI decision making using the MCTS algorithm with a clear visual feedback. Thank you for watching.